Welcome to Flash 101 from Pure Storage, our educational video blogging series on the basics around flash storage and storage performance management. My name is Matt Kixmuller. I'm the VP of Product Management here at Pure Storage. Today we're going to talk about one of the biggest misconceptions and concerns that I hear from people around flash storage, and that's the whole issue of flash aging. Basically, will my flash burn out over a certain period of time? While it's true that flash cells do have an aging effect, the way that that aging effect occurs is vastly misunderstood in the industry today. So let's dive in and understand a little bit more about how flash works, and then how as vendors we work to enhance the life of flash. So first, a little bit on just the basics of how flash works. Most people understand pretty well how a rotational hard drive works. Flash, on the other hand, is a completely different technology. You can think about flash very simply as billions and billions of little cells that are each capable of holding a charge. And so when we program flash memory, we charge it to a voltage. And that voltage, that act of charging it and then eventually discharging it, slowly starts to break down and destroy the cell. So it gets less and less good at holding that voltage for a longer and longer period of time. The first thing to understand about flash is maybe the difference between MLC and SLC. There's two broad types of flash. The highest grade flash is SLC, or single level cell. And that means it's only capable of holding one level of charge. The cell is either charged to a voltage or not charged, so you can go and read it and have one bit of information that way. If you look at MLC flash, or multi-level cell flash is capable of 4 states: no charge, or 1, 2, or 3 different voltage levels of charge. And so, as you can imagine, the multi-level cell flash is a bit more finicky. As it starts to break down, the flash gets less good at really determining which level of voltage is in there, and you start to see issues. And so the biggest challenge with flash is, as the flash ages, you start to see more and more errors. Now, flash has ECC inside that can go through and check for integrity errors, check for issues, and work around those in very sophisticated ways. But a simple understanding of this is that basically the more times you go through and you program and erase the flash cells, they slowly start to wear out, get less good at holding that charge, and can hold that charge for less time. Now, what most people start to think about lifespan, most of the flash cells will have a certain number of program erase cycles that are guaranteed by the manufacturer. That number is usually somewhere in the thousands. And the common misconception about flash is that basically, as you start to program it more and more, that you'll be going along, and once you hit that mystical moment that you hit the number of program erase cycles, the flash crashes and can no longer be used and is somehow completely damaged. And the truth is, that's not at all how flash works. What happens is that basically, over time, flash just gets less good at holding that charge. And so there's a given error rate, or a bit error rate, within the flash, and as time goes by, that bit error rate starts to rise. And what the manufacturers have done is they've picked a point in time and said, okay, that's the point where we're going to say this flash has had too many program erase cycles and it can no longer be used. But it's important to understand what that error rate means. What that error rate means is that there's a higher chance of bit errors, and those bit errors have a higher chance of occurring the longer time you try to keep a given charge inside that cell. And so it turns out there's a wide variety of techniques that manufacturers and vendors like ourselves can use to understand and manage and extend the life of these flash cells. So the first technique is to lower what's called write amplification, where in the background within flash, whenever you write, there's oftentimes other writes and movement of data that has to happen. So the less write amplification you have, the less that you're going to burn out the cell. The second thing you can do is you can understand longevity. And so basically, as this error rate gets worse and worse, all that means is you really can't keep data in the same cell of the flash for quite as long of a time. And so you have to move the data to refresh it. And so if you have an acute and kind of intense understanding of this, then you can understand the age and you can understand how long you can keep data there, and you can start moving the data around and refresh it in that way. And that can dramatically extend the life of the flash. And then finally, many of the vendors at different layers of the stack are inventing new forms of ECC that help understand errors, see integrity errors, and correct around them so that they get discovered and get fixed right within the flash itself. So if you take a combination of all of these different designs, it's possible to dramatically extend the life of even relatively lower quality consumer grade flash. And it's possible at this point to easily deliver a device at the enterprise level that can sustain dramatically expansive I/O loads and last 5 to 7 years, well within the typical deployment time of an enterprise application. So hopefully that gave you a good sense for wear leveling within a flash environment and that mystical cutoff point where the program erase cycles reach their end, how that doesn't actually happen, and how as flash vendors we can be very intelligent about managing the longevity and lifespan of our flash. That's all for today. Hopefully you enjoyed it, and you'll join us next time for Flash 101. Thank you.